let me just talk about one of the motivations for this first. Before, I might have a point in this program where we get to it again, but let me just talk about motivation behind this. When I started making the language, I decided to stay away from macros as much as possible, especially C-style preprocessor macros, because those don't play very well with debuggers. They're messy. They tend to cause a lot of problems, and you have to use a lot of weird hacks to work around the problems. And I wanted to say, okay, how much power can we make sure that the language has without resorting to any kind of textual overlay like that? And then maybe later, if we do a macro system, it'll be a macro system more like a language like Lisp has, where the macros are more something that the programming language understands, as opposed to something like layered on top, right? Layering is good because it lets you separate the things, but it's bad because the things don't know about each other. And when you're programming, you kind of want an integrated experience. If you're stepping around through code, you want to be able to step into a macro and step back out and so forth. So that had been my attitude from the beginning about maybe we'll do macros. If we do them, they'll be more like Lisp than like C. But we went for a long time without it because it was like, let's just see how good we could make the language without macros. But then at some point, I guess it was a couple years ago now, we'd have to look, we started to do iterators for data structures. And let's just go ahead and look at this data structure at first. We have whatever stream it was where I introduced iterators. It's on YouTube. And I go through this whole thing for like an hour. We're going to rush through it a little bit at the beginning. But like, here's a data structure. It's called a bucket array. And the way it works is there's just one memory bucket that holds n of whatever particular type of thing you want to put in the array. And we allocate one bucket at a time, and we have like an occupancy mask that tells us which of those things, which of those slots are in use and which aren't. And so you can add new things to the array without reallocating the whole array, right? You can take a pointer to something in the array, and you can pass that pointer around, and it'll stay stable as the array is modified, right? But you also just want to iterate over the array. And so I said, oh, this will be a good test for iterators. Let's make some hooks so that our native for loop knows how to talk to arbitrary data structures like this one, right? So I started doing that, and here's what we ended up with. And this is cleaner than C++ iterators would be, but like, I was not happy with how much code it was. So we made a type that's like an iterator that goes over a bucket array, right? This is a polymorphic type, or what you would call a generic in C++, because it's got an argument. It's like the type of the thing. And then we have some functions. And the way it works is that the for loop knows to look for these functions if you're doing a for on a type that's not a number, right? So it calls iterator make at the start, which sets an iterator to the beginning. It calls iterator next, and iterator get value. And then if you call remove on the loop, then this is how you define what should happen in the array. And this all worked. We used this in production on the game for like 2 years, but I was really unhappy with it because here's the thing. All I was trying to do, in reality, anytime I wanted to iterate over a bucket array, is actually this following thing. It's a 2-level iteration. There's buckets, right, on the array, and then each bucket has some number of slots, and if that slot's not occupied, then skip. Otherwise, just put whatever code you would do here, right? That is all I wanted to do every time. And so in some sense, the job of a custom iterator for this data type is just to encapsulate this knowledge so that we don't have to remember how it works and type it out all the time and maybe get it wrong. The knowledge that it's actually a 2D iteration and you've got to check the occupied mask, right? Now, how does this turn into this, or even more code if it was in C++? So I was unhappy with that. And so I'd been thinking in the back of my mind, if we have a macro system, one thing I want to do with the macro system is just write a macro that says, here's how you iterate this thing. It looks like this, right? And then your code just goes in there, and instead of having this giant thing with an extra data type, by the way, in addition to being more code, this is also slower because we have this extra data type representing an iterator, and you have to hope that that gets optimized out, which it probably won't in many circumstances. Yeah, it's a lot. Okay, so, this is what we actually want to do. That's all. And so I decided some time ago that this scheme of iterators would be unacceptable in the long term, but that we would just work with it for a while. So we did. Wow, everybody's loud down there. I might have to close the window. That's what I get for living in San Francisco. So, So we lived with this way for a while, but because this was such a headache, I didn't even make iterators for several data structures. So there's a hash table that I made, which was just a one-dimensional iteration, and where you would just check the hash, and hash value of 0 or 1 means unoccupied. And we would just do that manually every time, because I just didn't want to do all this stuff. All right, so that's the motivation. The motivation, well, among other things, of course, you want to be able to use macros for a lot of different purposes. But this was a concrete application that helped me understand whether I was meeting the goals or not, which is, can we just do this? That's all we want to do. We'll talk about the subtleties. It's not as easy as you might think. There are subtleties involved here. Okay. Now, leading into talking about macro features, we're going to actually not do a macro feature. This is a for loop feature, but it helps us plug into iterators later, right? So as people who have been following this programming language know, we have a very syntactically terse for loop, right? So here we've got an array of 3 strings called fruits. It's apple, banana, and cherry, right? A, B, C, fruit. And we iterate over that, and we're just printing 1 and then the item, right? And so that's all you have to do to iterate over a loop and do something. It's much less verbose than it is in some other programming languages. So if I run this, let's just go back up to the beginning. We're just going 1 apple, 1 banana, 1 cherry, right? And so that's what this is doing. And we have, for a very long time, had a syntactic way to reverse iteration on the loop, right? Which is just by putting this little less than in there. And then you go the other way. So for 2, we go cherry, banana, apple, right? The problem with that is it's only something that you can type, which means it's a syntactic feature of your program, which means you can't parameterize it. You can't have a parameter to a function that says if you want to go backwards or not without typing the loop twice and say, if backwards, do this one, otherwise do this one. And so there's always been a little bit of a disconnect there. So we added this feature where you can say, well, we're reversing or not, right? You can say less than, equal, and then that parameter, right? As opposed to just the less than here. And so here, fruits is going to go forward again. If I recompiled with this set to true, it would go backward. But we have a better example right here, which is here we have a function called print animals. We've changed to animals instead of fruits. We put a prefix in front, and then a compile time parameter that tells us whether we reverse or not, right? So this $sign means, again, when you call this with a constant, we bake the constant into the procedure and generate a separate procedure for each value of this parameter, right? So here we're going to print animals not reversing. So we're just going to go ABC with hello as the prefix. And here we're going to put sailor as the prefix. And we're going to do it in reverse order, right? So hello, ABC, sailor, CB, antelope. So that is an example of using this, right? Now this isn't a macro yet. This is just a regular procedure. Okay. Now, we also had this thing on for loop that's about whether you want to take the pointer to each element or not, which is very useful, for if you want to be data oriented about things, you want to store things by value in memory, as opposed to what a lot of modern, quote, modern unquote languages encourage you to do, which is to have them separately heap allocated. And so you very often want to have arrays packed full of data, and then you want to iterate over independent things, and maybe you want to modify those things, or maybe you want to pass them somewhere else. It's convenient to have a pointer. So you can do the same thing. You know, the syntax before, I didn't have an example of it, but you would say star to say by pointer. And now you can say false or true. So we've got the numbers 1, 2, or 3. We're iterating them. And here we're iterating the values. And here we're iterating the pointers to those values. All right? And that's controllable by a parameter in the same way. And so then we've got this function that does both. We could say it's a for loop. Maybe it's by pointer or not. Maybe it's reversed or not. Iterating over these computers and printing the prefix, and then whatever the value is of the thing that we're iterating, right? And so here I've made the prefix be the values of the variables. For f is for false in the first slot for not by pointer, and the second slot it's like not reversed, right? And so here we're printing the computers not by pointer, not reversed, right? Not by pointers and reversed. By pointers, not reversed. By pointers, reversed. Now these numbers are different from these numbers because we actually generated this procedure twice. And so we generated this array twice. And whereas we deduplicate individual strings right now, we don't deduplicate the actual array pointing to those strings right now. I don't know if that would ever make sense to do. But so those have different addresses, because it's 2 instances of a function. Anyway, so we buffed up the for loop. Now we're going to start talking about macros and then how that iterates with, how that interacts with macros. All right. Someone is saying the syntax looks really awful. Look, it's not final. And it's one of these syntaxes that it's actually nice when it's like this. It's very nice when it's like this. I agree that it looks a little messier when it's like this, but you don't really do this very often, right? You almost never do this, actually. So it's okay if things are less nice and you do them less often, in my opinion. But yeah, the whole syntax of the whole language may change at a later date. Okay, so let's start talking about another motivation for macros, actually. So the first motivation was to be able to iterate very cleanly. Another motivation was because constructors and destructors were not working out, as I mentioned in the previous demo, we took them out of the language. The one reason why it felt okay to take them out was because I wasn't using them very often. And the places where I was using them, we were really using them for destructor functionality, where the destructor was just a way to call something at the end of the scope. And it's like, well, if you could just insert something into your scope that had a defer statement, which runs at the same time as a destructor, then you could get by without destructors and still have that clean way of doing things. And so here's a second motivation. For example, say you want to have a scoped lock that like grabs a mutex at the start of a scope, and then you might exit out of that scope in many different places, and no matter where you exit out, it'll release the mutex, right? So here's an example. We say, hey, I'm entering this example. We open up a little scope in the middle here. We say lock this mutex, do stuff, do some more stuff, and then at the end of the scope, we'll release the mutex, right? So scoped lock here is actually a macro. It looks like a regular function in every way, but it has this word expand here. That's the thing that's different. Up here for a mutex, we've got a dummy struct, just like pretend it's a mutex. It's just when we lock, we print this, and when we unlock, we print that. So, well, what does this example print, right? So we say we're entering the example, we say locking, we're doing our stuff, we're doing more stuff, we're unlocking at the end of the block. Actually, let me put this over here and over here so you can see these, right? So we're doing more stuff, we're doing more stuff. and then we do unlock because the scope closes, right? And then we exit the example. So this lets us do the same thing as a destructor would have. Now, why does this work? Well, it's because when you put expand here, it turns a regular function into a macro. And it being a macro just means that these statements get inserted at the calling site like you might imagine, as opposed to living in a separate body somewhere that you call. Okay, that's a very straightforward example that doesn't really tell you anything yet. Because there's many different things that this could mean. Like a C-style macro, well, C doesn't really have defer, I don't think still. Maybe it does now. So we'll start getting into details of what's going on. So firstly, these are hygienic macros, just like in Lisp. So here we've got an example of a value. Let me just say what hygienic macro means. Hygienic macro means that just as if this was a function, right, it's got its own namespace with its own names for variables and stuff. And those are lexically determined by the scope of this. And when you use the macro, you can't see these functions or see these names. And you don't have to worry about the names. You don't have to worry about using things of the same name accidentally as the other thing, right? Yeah. Yeah, one thing at a time. I don't want to get ahead of myself. So here we've got a macro, and there's not really a good reason for it to be a macro in this case. We're just showcasing the fact that our identifiers don't collide. So we take a string, we concatenate it 3 times with commas in between and an exclamation point, and then we print that. We could have done that all in one print, but of course we wouldn't have had a temporary variable called value. So we call macro on developers, and of course we get developers, 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 right? But here in this scope, we've got a thing called value, and it's integer, right? It's a sum of integers, and we print that it's the sum of integers, right? So if this were behaving like a C macro, and this was just directly inserted into the scope naively, we'd get a redeclared identifier down here, because this value it would be a redeclaration of this, but that doesn't happen, and you don't have to worry about it. So you don't have to name the parameters of your macro funny names, or you don't have to gensim things or anything like that. Okay. Now, implementation-wise, macros work just like procedures, actually because they are procedures. Okay. As far as the programming language is concerned, a macro and a procedure are the same thing until the time comes to generate the code for the procedure call. Well, approximately. There are some syntax tree things that happen that are a little different. But in terms of the way that they interact with the rest of the compiler, they're actually the same thing. And that means that all of the features that we have for functions also work for macros just straight out of the box, right? So you get type checking on the arguments. You don't need to know where the macros are in your program. Just like functions, there's no declaration order constraints, right? You can overload macros with other macros or with functions, again, because they're just functions. They could be locally scoped. We'll show a couple more features in a minute. Anyway, so here's an example. We have 2 versions of foo. These are both macros because they're marked expand. This one is not a macro. It can't be a macro, actually, because it's recursive. It calls itself, right? So then we have this thing. We're going to say foo of high. That's going to call this overload, right? We're going to say foo of 2.5, 3.3, which is obviously going to call this overload. And then we're going to say foo factorial, which has to call this one. And, foo factorial is foo of 6, right? So that foo is going to be this foo. And we print that out. So let's just get through that first of all, right? boom, macro foo of string was given high. Macro 2 floats was given these floats. The sum is this, right? Foo factorial is 720. Okay. So now we have a fourth version of foo that's defined. Let's even find where it is. It says the bottom of the file. It's actually not at the bottom of the file now. Okay, it's down here. It's way down here. Again, just to show that there's no ordering, scoping constraints. It's a variable integer argument version. That is a macro again, right? And it just sums the arguments, right? So it's just, we're just going through the versatility of all these function things. Here's a locally scoped one. We can do that, right? So where are we? The varargs one, the locally scoped one. And just like functions, you can bake these, because again, they're just functions. So here, we're going to bake. So for the functional language people in the audience, baking is a compile time currying where you take the old version of this function and you generate a new version of the function with this value substituted, and then all compile time optimizations are applied because this entire function is computed at compile time, right? Not that it matters much for this function, but we're just going to show we're baking a version of locally scoped macro. It gives us a new macro where 69105 is hard-coded as this parameter. We're actually going to use this later in this demo. If this seems like a weird feature and you're like, what's that for? You'll see. But anyway, so then we call baked with no parameters because it used to have one and we baked that parameter and now it has 0 parameters. Okay, named arguments, just like functions. So here's a macro A and B. It takes A, it takes B. Uh-oh, I jumped ahead, so we're going to have to explain this feature. Oops. This is what happens when I rearrange the order in which I demo things a few times. Let's ignore that feature for a second. So we have A and B, it takes 2 strings, and we put them together with some join variable. Well, I have to explain. So it's a hygienic macro, so it doesn't have access to your variables, or you don't have to worry about namespaces colliding unless you want them to, right? So the backtick in front of join says, actually, let's refer to this variable from the calling scope, right, of where we're inserted. So here, we're making a thing called join. It's got like A spaceship B or whatever. And we're calling A and B with B as sailor and A as hello, right? We're using named arguments. So we're using just all this tooling that we have available for calling functions, and it works just fine on macros, the same as functions, right? So this wouldn't work on a function. You would have to pass join in somehow, but it works here, right? Well, you could almost imagine it working because this is lexically scoped here, but like if we put it outside this function, then it would surely have no way to see this. And yet it would still work because it's a macro that gets pasted in. Varargs, we already did varargs. I didn't notice that I have 2 varargs demos. Anyway, so here's a varargs that puts a defer, which is again gives it a reason to be a macro. It's defers and for all the values prints them. And so we're doing dimwit first and then flathead, even though the calls are in the reverse, because defer executes in stack order, which is what you want for destroying and closing things, right? So we do dimwit first, and then we do flathead. OK. So this is where I was efficiently really going to explain backticks. So here I've got a value. I've got a local variable. It's called value. It's bound to the string local. I've got a macro called backtick macro. And backtick macro says I'm able to access value. It is whatever, right? So we have a backtick in front of this. Even though this doesn't have anything called value in its scope, it's able to look up to the scope of the person applying it. Now notice this time it's not in function scope either. It's like at global scope. So really the only way that we're able to see this is because this is a macro that's being inserted directly into the syntax tree, right? Okay, where are we? I am able to access value. Here we go. I'm able to access value. It is local. So now we can have this backtick macro, and it'll look at both values. So here I have a value called value bound to the macro, meaning the macro scope. I've got another version of value out here still called local, right? And so here we're going to enter this macro. We're going to look at, this is just a label, right? So we're calling this with the label first or second. So we're going to say we entered first or entered second, and we're going to say what the value is. And this is just our value, right? But then we're going to say backticked value, and we're going to access the one from the enclosing scope. And then to give this a reason to be a macro again, we're going to use a defer at the end. Here we go. We entered first, value is macro, backticked value is local. Entered second, value is macro, backticked value is local. And then we defer close the second, right? And defer close the first. Okay. Are there any questions so far? Very on-topic questions. I've been glancing at chat. I've seen very off-topic things go by. But like questions about how this works before we go on, because these are like basics, and I'm speeding through it. I'm sort of assuming you know what a macro is. I'm assuming you know the pitfalls of C macros and why it might be good to do things this way and so forth. Can you use macro in macro? Yes, we will have an example of that later. Can you apply expand at the call site? There's not really a reason to do that. Expand at a call site would be the same as inline. Because if the body of the macro isn't written knowing that it's a macro, there's like no reason. Can macros have polymorphic arguments? Yes, I believe we have an example of that later. How does the macro backtick feature differ from a capturing lambda? It is different because we're not making a separate function, and that has a number of ramifications. One, you don't have to worry about getting optimized out. Two, you can use little snippets of code and pass them to macros in ways that are less bulky than you would if you had to make a lambda. We'll show that later. If the macro has its own scope, how does the defer happen on the caller? Well, it's a little bit magical, right? So what happens is there's a scope. The scope of the macro contains the macro's own names, but it's transparent to certain kinds of things. Defers is one of them, and we're going to go into another one of them in a minute. So it's not a naive separate scope, let's put it that way. All right, there's a lot of questions. I'm just scanning really fast for anything that might, like a lot of these questions are about things I haven't covered yet, so I'm going to skip those. Can you bake with a reference to a local? Any parameter to bake has to be a constant. That's the way it works. So if it evaluates to a constant, sure. Otherwise, no. Doesn't the backtick feature make it unnecessarily complex? Wouldn't argument make the code clearer? Well, if you can write something as a function, write it as a function. Sure. The reason the backtick exists is to do things. Okay. The point of a macro. Well, let's go back one step further. The point of a strongly structured programming language that gives you functions with very well-defined lexical scope is that that's a very good way to organize programs generally, right? It cuts down on mistakes. If I use a variable we don't just pretend it's empty string. We say it's undefined. Why? Because that cuts down on mistakes. It helps you produce code that is not very error prone. Okay. However, sometimes you just need a way to get out of that structure because it's much more efficient to do something outside that structure, or it's much more understandable even, right? That's why macros exist in C, is because sometimes you just got to do stuff that's not like functions, right? And that's why macros exist here. So if you're asking why all this backtick stuff, it's because it lets you do things that are outside of that normal system of strict lexical scoping. And that's useful. And we're going to show in the rest of this some of the ways in which that's useful, right? Okay, a lot of this is stuff that we're going to cover later. Can a macro return another macro? Yes, although I hadn't thought to demo that, but yes. They're literally just functions. Although you would have to apply it at compile time, otherwise it's just a macro, right? Okay. Let's move on. We'll do some more questions in a little bit after we've covered some more material. Okay, now you can also use the backtick to define things in the outer scope. So just like those defers were able to affect the scope of the caller, right? You can declare variables in the scope of the caller as well. So here we've got this thing called definer. It's a macro. It takes a value. We define a variable called negation in the outer scope that is minus that value. And then we just do some other stuff. We're going to square it and print something, right? So we're calling definer on 42. And then we're also just printing negation to show that we have a local variable defined called negation, all right? So where are we in the output? Value is 42, its square is 1764, negation is minus 42, right? So by using this backtick, we're able to define something in this outer scope. So what these are, as I go through the things that you do with backtick and some of this other stuff, these are more structured ways of doing things that you would do with C macros. Like very often you might make a macro that like defines a variable because you just need that to do something, right? This is a way to do that where it's not just a textual insertion, so you could step through this in the debugger, for example, right? If you step into definer in the debugger, you'll go here, right? And if you're here and you say, where's the declaration of that variable, it'll know that it's here, right? That's the benefit of doing things this way, as opposed to just like doing an arbitrary textual rewrite on your program that your other systems don't know about. Are the backtick variables still on the stack? Yes. It would be on the stack of definer test here. Okay, so let's do some more stuff. We have a special new data type called code that represents an arbitrary syntax tree in the programming language. And macros can take these as parameters. And using this thing called insert, they can put them into the body of the macro. So we'll go down here to inserter test. We're saying tripler. We have this directive called code that says make this syntax tree out of whatever's after. We're just going to put print hello sailor. We're going to pass that to the macro, right? The macro takes some code. It inserts it 3 times. So this is just a macro that basically turns one statement into 3. And then we call it, right? So we're calling tripler on hello sailor. We get 3 hello sailors, right? Now, you don't actually need this code directive if whatever is inside here already would have resolved lexically. Like if the variables and all that are already well defined, then the caller doesn't even have to know that this is getting converted to a syntax tree. He can just call. So you can just say tripler and then this thing, and it'll do goodbye sailor 3 times, like you see here. Now you can put arbitrary amounts of stuff in there. It doesn't have to look like something that you might usually be able to pass. So here we have a code directive. It's saying here's this whole block. Within that block, I'm defining some function called polynomial that takes a variable and computes x squared minus 3x plus 2. And then makes a variable, takes a random number between 1 and 20, and evaluates polynomial on that and prints that and the value, and do that 3 times. Okay, we're going to pick a random number every time because this is calling something that has global state. So here we go. Polynomial of 19 is 306, of 11 it's 90, and of 15 it's 182, right? So this just shows you we're passing in a piece of code. In another programming language, this might be something that you would have to make a function out of, right? Like a locally capturing lambda or whatever. Here, we are not doing that, right? This is literally just being pasted into tripler. And then the result of that is being pasted back in out here. So you don't actually have to worry about wrapping and unwrapping functions. You don't have to worry about whether something is going to get inlined, whether a constructed function is going to get optimized out, or whether the abstraction for it is going to decide to heap allocate like happens with standard function in C++. It just goes, right? All right, so here's something just like tripler, except it's slightly different. It takes 2 parameters, A and B, and it does A, and then B, and then A. So here we're calling that with it's pitch black, you're likely to be eaten by a GRU, right? So pitch black, likely to be eaten by a GRU, it's pitch black. Now, just like you have backtick that says, I want to reach outside the scope. So notice that all this code out here, actually we maybe could have had some better examples, but all of this code lives lexically in the scope of the caller, right? All this is code that makes sense to the caller. But you can also have a system where you define a macro that takes parameters that are code meant to actually go in the body of the macro and live inside the body of the macro. And when you want to do that, it's the same thing. It's code. We just insert it differently. We just say, insert this to be internal to my scope instead of in the caller scope, right? So then we can do tricky stuff like I can refer to the variables in the macro, like this index variable, which I can't see out here, and I don't know what it is, right? But this gets inserted in such a way. It's like an inverse backtick. Maybe it could syntactically look like the opposite of a backtick, but not really, because it's an insertion and not a variable reference. I don't know, man. But so that's how this works. So I'm able to make a parameter, right? That's just some code, and pass it to this macro. It uses variables in the macro, and it evaluates just fine, right? So where are we? Square is 1, 4, 9, 16, 25, right here. Okay. Why do that? What's the point? Well, again, instead of getting all functional programming brain, where you make a function that takes other functions as arguments every time you want to do something, and so those pieces of code have to be all super encapsulated, you can make macros that are just designed for you to fill in little pieces, almost like you're copy and pasting code into the macro at the site, right? And so here we have one called visit files. It's, again, maybe not the best example, but we take 3 pieces of code, a pre that we put at the beginning, a post that we put at the end, and then just pretend we're doing like a file search and we find these file names or something, right? For everything in those files, then we insert this, but we insert it internally. So the caller is like, knows what this macro is and knows what the variables are, and just can refer to file name and file index, even though those are not exported from the macro, but can use a backtick that refers back to this. So like, we know this is being inserted into the body of the macro, but we can also use our own variable by backticking it, right? So, so our pre is just starting, our post is just ending, and for every file, this macro, or no, this insertion to the macro is printing the file index, which is just whatever this index was from the iteration. But then also our caller count, which we start at 42, and then we add 1 every time, right? So the index in the iteration is 0, 1, 2, 3, and our caller count is 42, 43, 44, 45. Which again, this is just a way of, with more hygienic namespaces, being able to control what is happening and also having good error reporting over when you get things wrong. Okay. All right. So here's another example for convenience. Let me just put a little space here. So we're going to call a sorting routine. So we're going to make some numbers. We randomly generate them, and we say before sort, here's the numbers, right? So before the sort, here's the numbers. They're just numbers between 1 and 100, or 0 and 99, not in any particular order, right? And this is the index in brackets, and those are the actual numbers. So we're going to call this bubble sort. Now, you know, sorting in C and C++ is a giant annoyance because it's all based on like qsort from back in the C days, where you make a comparator function that takes like 2 types and it outputs a number that's less than 0 or equal to 0 or greater than 0. And then maybe in C++ you have templated versions of that maybe don't exactly use a function, but probably they do. It's all very lambda brainy, and it generates relatively slow code. And it's just a headache. Like, look, sometimes I don't want to think that much. Sometimes I just want to like sort stuff. So here I've got this bubble sort, and I can just say bubble sort the numbers, and the sorting criterion is just going to be A less than B. Now I know in the macro that A and B are the 2 things we're comparing, so I'm just saying, you know, sort things so that it, you know, in increasing order, A is less than B, right? And then if I want to do it the other way, I could do A is greater than B, right? And I'm just passing in this code. This code is being inserted at this point in the macro, and the rest of the macro is a bubble sort, right? So after the first sort, the numbers are this. They're increasing. After the second sort, the numbers are this, right? So we can pass code that is very concise and succinct to a macro because it's just getting pasted together anyway. This doesn't have to make sense by itself as a function, if you know what I'm saying. We don't have to like lambda of parameter A of some type and parameter B of some other type and whatever, and hope that that gets optimized. We just say A less than B, right? Okay. Let's get past our visit files and bubble sort. Oh, I did use this. Let's delete that comment. Okay. This is maybe a little bit of a nuance, but of course, in the same way that we were able to use the backtick to define variables, we can have the type to that be parameters, just like you would expect with a polymorphic function, except you don't even have to make this polymorphic, because like macros are automatically polymorphic in their arguments because they get compiled. They get expanded at compile time. I really can't speak today. I don't know what my problem is. So here we've got a variable called t that's a type, and hey, it's a macro, so we don't have to say $t. And even though this doesn't say $t, we can declare 2 things of type t. These are hygienic in the local scope, and then we make a thing baz that's the product of those, right? So we're going to make 2 floats, 3 and 5, and say what baz is, and then 3 signed 8-bit numbers, 3 and 5, and say what baz is, right? Where are we? Here we go. 15.0 and then 15. So again, if you haven't written large volumes of code, you probably are thinking, what is all this about? But like, this is the kind of stuff that you want to do sometimes when you want to do a whole bunch of things over and over that are a little bit different, but not that different. And you want to be able to control the differences, but you don't want to have to be like calling functions. You just want to like declare some variables or whatever, right? This is how you do that. Okay, now I started out by talking about for loops, and now we're going to get to the for loop part. So for loops now, instead of having this protocol where they call make iterator and then get value on the iterator and next on the iterator, the for loops now, when you for over a custom type, it just calls one macro. It's called for expansion is the default name. We'll see in a little bit that you can actually change the name. We're just gonna, oh, I already did that. I have a comment here to look at the old iterator stuff, but we did that at the start. So if you want to iterate over any type, you define a thing called for expansion that's got 4 parameters. It's got the thing that you want to iterate over, right? The body code, which is what the for loop passes in, that's the thing that you want to paste in order to iterate. And then 2 control variables that says whether you want to take the pointer to each thing and whether you want to reverse each thing. You don't actually have to support those. You're free to ignore them. But part of the protocol is that those are passed to you, right? So here we're just ignoring this by pointer and reverse stuff. And we're just going to say, we're going to make an iterator for vector 4, and it prints cowabunga. That's a really stupid iterator, but it does. We're going to give you back a variable called it, right? Which is the standard. Remember, if you do a for loop and you don't name the variables, you get things called it and it index. So this is saying, hey, you have a thing called it that gets v.x, and then we're going to insert the body of your iterator, which is this thing, right? And then we're going to assign it to v.y and insert the body in v.z and insert the body in v.w and insert the body. This is a really dumb iterator. But it's just showing you how this macro functionality that I've talked about so far plugs into the for loop stuff in a very simple way. So here we go. We assign x, y, z, and w here, and then we for over this, and we get those. And there we go. That's all we had to do to make a for loop was this. It would have been way more painful and annoying to do it using an iterator making scheme. Okay. Let's go back to the bucket array. Remember, I said at the start of the stream that this is all we really wanted to do when we for over a bucket array, right? The actual iterator is a little more complicated, but not that much more complicated. Here it is. And in part, it's more complicated because we're handling taking things by pointer and reversal. But this is the amount of code that it is. Actually, it's got a little bit extra because this is like a feature that we wanted to use in the Sokoban game that doesn't really have to do with actually iterating. So really, without our hard-coded thing, it would be that. But we'll start talking about some of these other features of integrating with for loops. Oh, actually, we'll ignore this, actually, because it's got some features we haven't talked about yet. So we get an array of strings. For each string in this array, we add it to this bucket array, right? We're just going to show here that it works. So for every item in the loop, so note, first of all, that we're renaming. This is not called it. This is called item. And so part of the protocol of how for interfaces with a macro has to negotiate that name. But so every item is called item. We're going to use a defer to say this should print at the end of each loop. Then we're going to say we're about to say something about x. And then we're going to go 4 times and just say x is whatever, or 3 times. We're just going to print x is 1, x is 2, x is 3 for each item. We're not printing this string at all. Let's print the string. Like we should use the item, otherwise why are we frickin' iterating over the item, right? Okay. Maybe that makes this less readable, I don't know. But so we go, there are 69105 leaves in the pile, right? So we're iterating each of those things. We are about to say something about x. We do it and then print at the end because it's a defer, so it gets popped down there. However, Remember at the beginning we said there are some subtleties. For example, if you're going to iterate over this bucket array, you need to start thinking about what the loop controls actually mean. Because if you replace a one-dimensional iteration with a two-dimensional iteration, break and continue need to start doing different things. Because a continue, maybe it's fine if it goes in the inner thing, and a break maybe needs to go to the outer thing, right? Those sort of, the iterator knows what's right. Like your data, it's probably different for every data type, but the for loop needs to let you interface and control with that stuff. Let me just show for right now that that works in a very basic way. So here I've got my, okay, so let's clarify what's happening here, right? This A is our bucket array, which means this for loop is a custom for loop that calls our equivalent of this iterator. This for loop is not a custom for loop. This is just over integers. So down here, we don't want to continue over the integers. We want to continue out of the main loop. So let's first of all show that that works. And if it works, we won't print 2 or 3. Because by continuing out here, we're going to skip 2 and 3 after we do 1, right? So hopefully I'm just not totally lost in the weeds and people get what's going on. But here you go, x is 1, x is 1, x is 1, x is 1, right? OK. So we're just sort of showing macro-driven for loops interacting with non-macro-driven for loops and that sort of thing. Let's show it working with these, right? So first, we're just iterating over the bucket array, just printing out all the things with an index. So we're not doing our inner loop, right? So we're saying there are 69,105 leaves in the pile. We're going to iterate in the reverse direction. We get this handy, very terse syntax that I like using. And when we do this, what happens is, let's go back to our actual thing. What happens is true gets passed in this parameter, right? And then remember, as we opened with, we are able to do this thing very tersely to control the direction over which we iterate the loop. And for this data structure, it happens to be correct that if we want to reverse, then you reverse the outer loop and you reverse the inner loop and you just go, right? And if you want to take things by pointer, similarly, this thing right here. And then this, like I said, that's our own thing that we use in the game. So it's a data-oriented thing. Somebody remind me to explain that at the end, because I don't want to go into it right now, but it has to do with just being data-oriented. OK, so we go forward, we go backward, and we go by pointer to all these elements, right? And so we have a very nice terse syntax for doing all these things. Now there's this name remapping that happens that I've sort of been tangentially referencing here, right? So here we have a two-dimensional for loop. These are both custom for loops that evaluate that macro. So we're evaluating this macro here. That gives us 2 dimensions of loop. And then we're doing it again inside, which gives us another 2 dimensions of loop. So we've actually got a 4-dimensional iteration here. And in this version, we're going to break S2, which should break actually from here. And here we're going to break S1, which should actually break from there of the outer loop and not the inner loop. And so first let's show that that works, and then let's talk about how it works. So here we're going over every S2, or no, we're going over every S1. Let's talk about what S1 and S2 are. They're just the strings, right? And then I1 and I2 are the indices. And the I1 and S1 are the indices and strings for the outer loop. I should have maybe called them outer. I don't know. So here we're iterating over everything in the outer loop, but we only get to element 0 in the inner loop. And the reason why is because we break from this loop already. This break, named break, is something that we already supported. way back for vanilla non-custom loops, but now it actually just works here. So named break here lets us break from this or this. So in this second example, we're breaking out from 0, 0 right here. All right. So you might be saying, oh, well, actually, hold on. Let's talk about why this works. The reason it works is because when we insert code for a loop control, we're able to replace a few things. Like the standard loop control primitives, break, continue, and remove, we can specify what they should be replaced by, right? So we're going to insert something. We're going to say, all right, we're going to insert body, but if we ever see a break, we're going to replace it by break bucket, which breaks us out of this outer loop. That's how the named for loops work, is you say the name of the iterator. And if you say remove, we're going to replace that with this piece of code that just sets the occupied flag by false and reduces the count on the number of elements in the thing, right? And so you can think of this as being like a wildcard search and replace that operates on the piece of code that is inserted when this macro activates, which again is just whatever's in the body of the thing. Now, why does the two-dimensional one work? Because like doesn't this, when you expand the outer one, doesn't this replace the break in the inner one? And the answer is I think the answer is, oh, we only, the identification of this identifier with which loop controls whether the expansion actually applies, right? So when you say break S1, when we're expanding S2, we say, oh, that's actually not a break for our for loop, so it doesn't match for the purposes of that replacement. Same thing here. When we do this, we see this break and we're like, oh, that's a break, but it's not for our loop, so we leave it. Okay. So you might be saying, wow, that sounds like a lot of very custom things that only apply to this one case. And it's like, no, actually, it's been very carefully designed to apply to as many things as we can make it apply to. So let's show some more examples, and then maybe it'll make more sense. These are all examples that we use in production, by the way. So that bucket array, this new iterator down here, is what we use in the game now. We've been using it for a few weeks everywhere. We've got my hash table that I did. That's a port of Sean Barrett's hash table. Here is our iterator for the hash table. It's actually simpler. It only needs a one-dimensional array. It supports taking things by pointer or by reversing, right? It gives you this variable called it, which again, you can rename if you want. The way it works is I didn't explain this, but your iterator always exports values called, or names called it and it index. And then the for loop itself, when it goes to expand the for loop, knows if it needs different names and it changes the names, right? So this always says it and it index, but the names that you get are, for example, value and key here, right? So this is actually very concise and very nice. So you reverse or not, you take by pointer or not. And remember what I was explaining, that we would do this by hand, because all you really need to know is if the hash value is less than a valid hash, then you don't iterate that, right? If it is greater than or equal to a valid hash, then we set the index to be the key, right? Which is, by the way, of any type. This isn't necessarily an integer type. So you have a value called it, that's the value. You have an it index, that's the key. And then, I don't know why I put these braces here, but we insert the body, which is whatever your loop is. But if you say remove, then we replace remove by saying, oh, Well, we just put a special hash in the table that says this item's been removed so that further iterations will skip it, right? So here we're going to iterate the table. We're going to print before it's got a key and a value. And then we're going to say if the key happens to be this thing, 69105, remove that value, right? And then we're going to iterate again and make sure it's removed. So here, before leaves in the our 69105 pile there. It's in a random order because it's a hash table, right? And we remove the 69105 and we get that, right? So we do all this custom for loop and removal and ability to reverse and go by pointer or not. We get all of that in an iterator in that many lines of code, right? Which is kind of crazy, but it's good and it works all over the place. So here we've got a binary tree. Say we want to iterate over a binary tree. Is remove a special word in the for loop context. Here, it's a special word. If you want to talk about arbitrary pattern matching and replacement, there's a reason why I said we're going to have to break this demo into 2 parts and cover part of it later because it'll be too long otherwise. Okay. Iterating over a binary tree. We're making this thing called a tree node. It's a polymorphic type that takes any value type, right? So it's got a left element, which goes to a tree node, a right element, right? This is a very textbook binary tree. Because we're going to be data oriented, we're going to have an array of nodes instead of newing them. So we've just got 6. We're going to make names for them, A, B, C, D, E, F. And then we're going to set up the links in some way. And we're going to give the values, right? So the values are all names of famous countries like Belgium or Albania or France. And we're just going to iterate over these and print out the values. Here we go. What's the iterator for this? Well, we have it down here. It's just a map. We don't bother expanding, we don't bother supporting reversal right now because this isn't a particularly ordered traversal. So we just assert that you didn't call it with reverse true. We just pop a tree node on the stack, and then we have a while loop where we pop a tree node off the stack. If it's got a right neighbor, put the right neighbor on the stack. If it's got a left neighbor, put the left neighbor. And then, well, if we want it by pointer, define it to be the pointer to the current value. Otherwise, define it to be the current value. And then insert the body, right? So here's a for loop expansion for that for loop. That's, again, very simple. This is pretty close to the minimal code that you would write for a pre-ordered, no, this is a in-order traverse, no, pre-order. I don't remember. I think it's pre-order. My textbook traversals are a little bit confused. Somebody's asking why not use insert internal in the for expansion macros. The reason is because you don't want to think about, the whole point that this is a macro that lives somewhere else is you don't want to have to care what the names are internally. So you don't want to have to worry about colliding with the names, right? That's why it's not internal. Although you could, I mean, this macro could decide to make it an internal insert. I just don't think that's a good idea, right? Okay. So that's the thing that is then printing out these countries in no particular order. All right. Well, let's go to another data type just to show how good of an approach this is. Because I realized while I was explaining it, it maybe sounded like a bunch of weird features that were complicated. But it's actually not that much once you know how it works. And it applies to a lot of different cases. So here's another thing that we use in production right now, bit array. Which is a data type where if you just want to have a whole bunch of Booleans, effectively Booleans, then you maybe want to pack them into an array of 64-bit numbers, right? And then you can just ask if a particular bit is set, right? And then you have these accessor functions that just set a bit or clear a bit or whatever, right? Great. You can set or clear all the bits. So what does a for loop look like for that? I wrote a version, let's take out the comment for a second so we get syntax highlighting. I wrote a version that wanted to support reverse. By pointer doesn't make sense because they're bits. You can't really have a pointer to a bit. And if I gave you a pointer to a manufactured Boolean, like that wouldn't really make sense. So we're asserting that you don't call this with pointer. And then, sort of the cleanest way seemed like doing two different loops for if it should be reversed or not, right? If it's not reversed, it's very simple. Go iterate over every slot. It's kind of not unlike the bucket array. Iterate over every slot. Start a bit at 1. Iterate over every bit. Make a Boolean that's whether the bit is set or not, right? Insert the body. We actually don't need these braces. We used to need those syntactically, but now we don't. So this was living in a comment, which is why that hadn't been cleaned up, I think. Anyway, so you insert the body. And if somebody tries to remove a bit from a bit array, that doesn't make any sense. So we just say we don't support that, right? But break needs to break from the outer loop again because it's 2D. It's a very common pattern that you need to turn what looks like a one-dimensional iteration to the user into a 2 or more dimensional thing to iterate over your data structure, right? And that's why this replacement facility makes a lot of sense, right? OK, so then we shift the bit 1 every time we add 1 to the index, and we stop if we've reached the maximum number of bits in the array, which is not equal to the number of slots times 64 because the slots are like an over allocation, right? So if you have 72 bits, you're going to have 128 bits worth of storage, but you don't necessarily want to iterate over all of those, which is why we stop here. All right. So essentially, this is the iterator, but supporting reversal makes us do it twice. And then I was experimenting, and I was like, well, let's make a one version that iterates once and is less code. It's definitely less code, and we do things in various places, whether we want to reverse or not. But it's a little harder to understand. Like this, I think you can look at and understand pretty easily. So I'm not sure which of these I favor. You could just say, screw it. I don't want to support reversal at all, right? And so you could just do this one. How do I, there we go. And maybe this is the right answer, actually. Because do you really want to support reversal for a bit array? Well, I did in this demo because if you're storing an n-bit number, the way the bit array stores it is like left to right in the array. But if the way that we write these is the least significant bit goes on the right. So where are we? We're up here. So I'm iterating over all the bits, and I'm casting the Boolean back to an int, which is going to give me 0 or 1, and just printing the ints without new lines, which is giving me this, right? So those are the bits. You can see we set bits 3, 7, and 11, right? This is 3 from left to right, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But if you wanted to read this as a binary number, you kind of want to write it that way. So that's what the reversal's for. So bit 0, 1, 2, 3, 4, 5, 6, 7. This is the way that you would normally expect to read it if it's being treated as a number. Now, and then here I just print it out as Booleans as well. Now, do you really expect a bit array to be like, I don't know if you need reversal. So it's sort of the exercise that I've been engaging in applying these macros to these different data structures is in trying to get down to like, what's that minimal code, right? And the macro system helps us get down to something like the minimal code, right? So if you look at this one, this is approximately, if you were to hard code an iteration, what you would write. And this one doesn't support a reversal, doesn't support a pointer. It's pretty clean and pretty understandable. And in this case, then what adds the complexity is just if we want to do a more complex job, which I guess is good. But I have this sort of philosophical struggle that I'm having here about like, OK, if I'm implementing this data structure for bit array and I want a lot of people to use it, do I implement the version of the iterator that's capable and understandable? It could reverse or not and is easy to understand. Or do I implement the one that's less code but is a little harder to understand? Or do I just say, screw the reversal. This is just going to be a little bit of a gem of the iterator, and we'll just assert if you try to reverse. And I'm leaning toward the version that doesn't support reversal because, the more I've been programming, the more I've come to the attitude that having large volumes of code that do anything you might ever want to do is often part of the problem. And it's better to have code that's understandable, that does the thing that you want to do in a concise and clean way. And then you'll understand what the data structure does and how it works. And then if you need a version that's different, you could maybe just copy and paste this somewhere else, right? So those are the things that I'm just throwing around and that are up in the air in terms of the implementations of these data structures. But what I wish to show for this is just that, there's one more. The most concise one is the modern programmer version, modern programmer, where it's a one-dimensional loop, and it even supports reversal, and you just go over all the bits in the array, and you use the subscript operator, right? And you assert on remove. This is actually the shortest syntactic for loop version that I found for this bit array. And it actually works. It's just if you do this one, you're depending on the compiler optimizing the array subscripts, which maybe it is. So it would be interesting to use this version. Actually, I don't know if we say inline on this. We don't say inline on the subscript. So you actually would probably want to say this. It would be interesting to see what the generated code looks like for this in the end. Maybe this is totally fine. And it might be that this is just as good as this or any of the other versions, and it even supports reverse. So there is some universe in which this is the iterator for this thing, and that's just an amazing universe, because that's like the cleanest possible iterator that you could think about. Okay. I got a little bit in the weeds on that one. But the point is, you can do in this number of lines of code what it would have taken many, many lines of like C++ style stuff to do. And it's up to you whether you want to do this concise version or this longer version or this longer version or this longer version. And in the past few weeks, I've been playing around with all of those. This one is the one that we're currently using in production, although we don't actually use the reversal in production. We're just using the reversal in the demo. Okay. So now, like I said before, though, you might not want to use this iterator called for expansion. You might want to write your own iterator for somebody else's data structure that does it in a different way. Or you might want to provide several iterators for your data structure that do slightly different jobs, right? So let's make a much bigger bit array. It's just going to have 4 bits set, 364, 375, and 999, all right? And we're going to use an iterator that iterates over only the bits that are set. We don't care about the 0 bits, right? So we've got this iterator called onlySet. What does it do? Well, we're not going to support reversal right now because whatever. That's a complication. We're going to give you a value, it, and that's always going to be true because we're just sort of doing this for compatibility. Like, you probably should know that the value is true because you're asking to iterate over only the set bits, but there it is. It's true. And then, we iterate over all the slots in the bit array. If the slot is 0, then we know that none of the bits can be the ones we care about, so we just skip. So actually, in some sense, the whole point of this macro is this line, right? It lets us skip past a slot very quickly, right? Otherwise, we start with an index that's the slot index times 64, and then our it index is that plus whichever part of the loop we're in, right? Again, just like before, we start our bit out at 1, we shift it left, one every time, and we insert the body of your code, right? And so when we do that, here we go. Iterating only the set bits, 3, 64, 375, 999. Now, what if you want to only iterate the 0 bits, right? What do you do there? Well, you could write a version of this that's only unset. And you change a couple things in the function. Or you can write a more general version that's got an extra parameter. So here I've made this thing called only set or unset, right? And it has a target value that's a bool. And the target value says, are we searching for 1 bits? If so, that'll be true. Or are we searching for 0 bits? If so, that'll be false. And I was able to do this for this data structure with almost no additional code, right? Here's what we do. Again, we set it to our target value now, which would be true or false. And it's kind of stupid that we do that. But again, it's just convention that we're giving you a value called it every time. And then the only change between the previous version is if target value is false, we flip all the bits in the local value of the slot after we read it. So we don't modify the original data structure. This is a static if that gets evaluated when the macro gets inserted. So it has no runtime cost at all if this is false because it's not even there. If it's true, then the only cost is this additional instruction. So then if the slot's 0, we continue, blah, 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 right? So down here I have these underscore versions because I wanted to demo both of these. So we have this version that called only a set without an underscore, and then these with underscores that are defined as baking only set or unset for a given target value, right? So this has 5 arguments. Once we bake out the target value, it has 4 arguments, which is the right number for an iterator, right? I don't know if we should call these iterators, but it's the terminology I'm used to. So only set is only set or unset with true. Only unset is only set or unset with false. These are both still macros, just like before, and they expand out as you use them. So here, we're using our underscore version of only set. So it should produce the same output as this one. And then, OK, if we say only unset on this whole array, it's going to give us 996 numbers, which is too many. So I decided to toggle all the bits in the thing and then iterate over only the unset bits. And it should be the same numbers, except now they're unset instead of set, right? Just to prove that all this works. And there we go. Set, set, unset, right? This is a very clean and elegant compile time, provably not adding lambda closure style overhead, way to iterate over a data structure with the same efficiency as if you'd hard-coded it by hand, right? That's the point of all this. OK. These actually, by the way, when I do these assertions, these probably should be compile time asserts, because then you know when you make the mistake. So here we compile, but if I decide to try to reverse my only set, this should give me a compile time error. Oh, it didn't. Oh, wait. Did that one? Sorry, this is the other version. I got confused by the naming. This one is this one, which still only has the runtime asserts. I had a little demo panic there. All right. So there we go. Compile time assertion failed. Here, we're asserting that it's not reverse, right? And so then if I do that, but I do this on only unset, again, we'll get a compile time assertion. Line 232 this time instead of 207, right? OK. This is great. Now, well, let's keep going. So in the same way that we could define different iterators now, oh, I forgot to mention, right? Of course, I sort of glided over it, but the way that you specify the name is just with this colon in the for, right? You just say colon and then the name of the iterator you want to use. And that works syntactically with these things, right? It's just another one of those things. OK. So remember that back when we iterated the binary tree, it didn't go in any particular order, right? Which one was the? It was all the countries was our binary tree. How frickin' far back was that? No, that's. OK, it was here. So we were iterating these, but our iterator wasn't trying that hard to be ordered. So, and in fact, it was like a pre-order traversal, I guess, which doesn't really mean that much in terms of treating the tree as a sorted thing, right? But back when I did my hand concocted tree assembly, I assembled it so that the countries would be in alphabetical order if you did an in-order traversal left or right, which is also what the output of a binary tree constructor might do, right? So here, instead of doing the pre-order traversal, we can do the in-order traversal on our tree root and print in order, and you note that we get the countries in alphabetical order now, right? Let's look at that for a second. It's very close to the same thing. It's just a different iteration. It's a few more lines because it's just a little. So when you take computer science class in college and you learn about binary trees, you learn about pre-order and in-order and post-order, and they're usually defined recursively. The problem with doing them recursively is it's kind of inefficient. And again, it forces you, if you want to pass an operation to that, you have to define it as a function to pass in. Here, we don't have to define it as a function, right? Again, it's a macro. We paste it in. So this is our pre-order expansion. This is our in-order expansion. And the main difference, aside from slightly juggling things around, is that you basically chase down the left side of the tree first whenever you can, and then you go to the right when you can't go left, and you recurse back up. Anyway, so this is an iterative version of a pre-order traversal, iterative version of an in-order traversal. All right. So what if we want to be able to reverse that? Sometimes it's very easy to implement, right? Like with that bit array version where reversal was hard and annoying because it was so many lines until we decided to use the subscript operator, and then it was like very short. Here, we have this thing called reverse, right? And we're going to basically just say, instead of saying node equals node dot left and node equals node dot right, we're going to say go left or right depending on the value of this. And we knot it here and we don't knot it here, so we go in opposite directions. So if we're not reversing node equals node dot left, otherwise node equals node dot right, and if we're not reversing node equals node dot right, otherwise node equals node dot left, people were asking, can you call a macro from a macro? And the answer is yes. We made this macro called left or right. It's in fact locally scoped helper, and it's got a static if so that we don't incur compile time cost or runtime cost. And we say, have I been saying compile time cost the whole time? Sorry, runtime cost. There is no runtime cost to this. If left, we pick this statement, otherwise this statement, right? This is a very much more structured than C. It's easy to know when you make a mistake. It's hygienic, and yet it does all the right things. So this iterator supports both reversal and taking by pointer or not. That part's easy. That's right there, just like before. So here's our in order with the countries in order, and here's our reverse with the countries reversed, right? Whoops, that's done right there. And I think, that's almost everything I wanted to demo. There are some questions like, what happens if you concoct infinite insertions? So for example, here I've got A and B. I don't actually use A in here, or I don't actually use B, sorry. I just insert A. I don't know why I put B. Oh, right. Yeah, it's there. Let's do this. Yeah. So basically, so A inserts B and B inserts A, and we insert A, right? So, well, that inserts B, which inserts A, which inserts B, which inserts A. So the compiler is kind of in an infinite regression, right? And it's just going to say, like, look, you just can't do that. I think I set the limit right now at like 100 deep, but it's going to be configurable at compile time. So the answer is you get reasonable messages for some definition of reasonable when this happens. I think that's everything that I wanted to say. So I'm going to take a voice break for a couple minutes. I'm glad I didn't try to do everything. OK, so to recap, this is the start of the macro functionality. We haven't covered today how this integrates with the metaprogramming features from like the user level extra workspace metaprogramming stuff. That'll be next time. And we haven't talked about more generic like search and replaces on user code. The only search and replaces we've demoed today are these. That's also going to be next time. So don't really ask about those. If you have other questions, question and answer time. Address questions to me for max visibility. And I'm going to take a 4-minute break and just make some new tea and stuff and get my voice back. And then we'll continue.